Okay. So as I have said just a minute ago, if you don't have the printouts, these printouts, make sure to get them. One of these. Is there anyone who doesn't have these problems? There you are. Anyone who doesn't have these? So today we are going to, here you are. Today we are going to finish chapter 3 and we'll start solving these example problems. These example problems are also posted on Blackboard. These are book problems, the same as we did before. The only difference is I thought it may be a good idea to print out the text of the problem. It will help you better follow the solution. So I think the last thing we talked about in the previous lecture was, what was it? It was the flow rate measurement, right? The idea was we can find the flow rate using this formula divided by rho 1 minus A2 divided by A1 squared. Okay. This is a formula we derived for some type of a Venturi. It can have any different type of Venturi. And using this, you can find the total flow rate inside the pipe, right? Or a Venturi, or whatever type of pipe is that. You essentially, let's say this is your point 1, point 2. If you have the properties between point 1 and point 2, essentially the pressure differential and A1 and A2, the areas, you will be able to find the total final flow rate. There are different devices that we use like this to measure the flow rate. The first type is called an orifice. Let's make sure the spelling is correct. Yeah. For orifice at part 2, you have this type of constraint, right? A2 is going to be the area here, A1 the area here, and you can measure the pressure differential using a manometer, right? It should be the other way around. And we can find the flow rate using it. Another type is a nozzle, very similar to orifice. Just the orientation of this constraint is going to be different. And the last one, which I think we talked about in more detail, is called the Venturi. Point 2, point 1. For this type of pipes, we will be able to measure the flow rate using this equation, right? How did we derive this equation? We essentially use Bernoulli's and the continuity equation for an incompressible inviscid flow. Okay. I think we talked about this, right? Okay. So moving on, there are other types of flow measurements. I don't know if we talked about this part as well. Let's say you have some sort of a gate, like open surface gate. You have water here, free surface, and the water is flowing out from here. And you want to find the flow rates of this type of design. We can again apply the Bernoulli's equation and use the continuity equation to find the flow rate here, which is going to be equal to Z2 divided, I'm going to tell you what Z2 and B are, 2G Z1 minus Z2 divided by 1 Z2 Z1 squared. I think we talked about this as well. Just a reminder, this is going to be your Z2, and Z1 is going to be this height. Okay. But the question you may want to ask yourself is that, is there any, is the type of wall here, whatever you want to call it, is this going to make any difference? Because let me magnify this part. Let's say we have this type of wall. We can have this type of well-rounded wall, right? Or we can have a very squared off type of pipe, okay, that the water is coming in. Is this type, is how we have manufactured this entrance of the pipe, of the smaller pipe, it is going to affect the flow rate. And the flow rate that we are calculating. And the answer is yes. Okay. This is going to affect the flow rate. But why is that? Essentially, the reasoning is very simple. Right? Here, when you have the streamlines going in, the transition is going to be very smooth, right? So the flow is always attached to the walls. And when you write this continuity equation, right, this was the continuity equation. The area you are using has to be the flow area, right? Which is essentially the same as the pipe area in a well-rounded pipe, well-rounded entrance. But in a squared-off entrance, you will definitely get some flow that is going to separate from the wall. So your fluid is going to cover an area which is smaller than the pipe area, right? If you have this area, the area that is covered by the fluid, the same equation applies. But we usually don't have that. What we usually have is the area of the pipe. So what should we do? How can we measure the flow rate? How can we apply the continuity equation? Essentially, what we need to do is to multiply your flow rate with a correction factor, which is called the contraction factor. And this contraction factor is given to you for different types of geometries. So whatever flow rate you calculate, you're essentially assuming that your entrance here is a well-rounded entrance, and your fluid is going to cover the whole pipe. Calculate using these equations, calculate the flow rate, and then multiply it by a correction factor, a contraction factor. So what is the contraction factor for different types of geometry? For a squared off geometry like this, the contraction factor is going to be 0.65. 0.61. We have another type of edge that is like this. Again, you are going to get the same effect as the squared off edge. Contraction factor for this is also 0.61. You may want to ask, where did we get this contraction factor? This is essentially based on experimental analysis. And it's the value of this length compared to this length, right? So this value is telling you that 39% of the area of the pipe is not going to, the cross-sectional area of the pipe is not going to be covered by the fluid. This is at the beginning, okay? When that's at the entrance of the fluid. Another type of edge that we are going to get is this type, which is the worst edge when it comes to efficiency of this type of flow rates. C of C here, the contraction coefficient is 0.5. So the area covered by the fluid is going to be half of the area, the cross-sectional area of your pipe. Okay? Is there any questions? Okay. So let's move on. There is another type of flow measurement that we can use for an open channel. It's called using a weir to measure the flow rate. What is a weir? You essentially have your open surface like this. Then you have a wall in front of this open surface, and you will get water flowing into this, over this wall, right? The flow rate here is calculated by this equation, C1 multiplied by H. I'm going to say what are H and B and 2G H. H here is this height. And B is going to be the width of your wall, whatever that is. Is there any questions? So these are all of the applications of Bernoulli's equation in different environment for different use for different applications. Flow measurements, we saw all of the different, yes. B is the width in this direction, right? In this direction. Right? So your wall is going to be B multiplied by whatever this height is, H. Yeah, so we have seen the different applications of Bernoulli's equations everywhere in fluid mechanics. But the next step is going to be essentially looking at Bernoulli's equation from a different perspective, which is, as I think I mentioned, this perspective is a little more common in civil engineering, and we are just going to mention it here. If you recall, we introduced this form of Bernoulli's equation as well, using all of the heads, right? It's constant, right, on a streamline, and the constant is called the H, right? The total head, right? We have the velocity head, pressure head, and the elevation head, right? Elevation head, I think we mentioned this. Velocity head and pressure head. This form of representation of the Bernoulli's equation, it's just a different form. It's the same equation. We just have divided everything by gamma, which is your rho g, right? And it is more common in civil engineering. But what we can do using this type of presentation is to define the hydraulic grade lines, or HGLs, and the energy lines. Or EL. So HGL and EL. Energy line is your head, H. right? So for example, let's say you are dealing with this type of flow. You have an open surface. Your energy line here is going to be the combination of P over gamma, V squared over 2G, and Z at each point, okay? So what does it mean? Let's say, what will be the difference in energy line between point 1 and point 3? The idea is for this type of flow between point 1 and point 3, your energy line shouldn't change. That should remain constant. So you can have, let's say this is your energy. You can have your EL. But the hydraulic grade line is defined as P over gamma plus Z. So we are removing the effects of velocity here. Okay. How would the hydraulic grade line look for this specific example? Or how would it change as we move from 1 to 3? The only difference between an energy line and a hydraulic grade line is that we are removing the effects of velocity, right? That's the only thing that's being removed. Okay. So at this point, and let me call this point 2, right? So what this means, removing the velocity, what this removing the velocity means is that your hydraulic grade line is going to change when your velocity changes, right? Why? Because this will represent your hydraulic grade line. And if you move the velocity, we cannot just remove it, right? You're essentially moving the velocity to the other side. So this H, this head, is going to change with the velocity. So wherever you have a change in velocity, your hydraulic grade line is going to change, okay? So do we have any change in velocity between here and here? Between the free surface and the entrance of this pipe? Yes, right? How can we determine that? Continuity, right? A1V1 is equals to A2V2. So your hydraulic grade line starts here. We don't have any other color. It starts here, and since your velocity is increasing, because area is becoming smaller and smaller, your head is your total hydraulic grade line is going to drop, right? So we'll see a drop. But what will happen between point 2 and 3? Your head H is not changing. That was the idea. What about velocity? Is velocity changing between point 2 and 3? Any ideas? No, it is not changing. Why? What is the equation we have between the velocities, for the velocities between these 2 points? Area is the same, exactly. Right, this is the continuity equation. So A2V2 is equals to A3V3. A's are the same. V2 is equals to V3. So your hydraulic grade line is going to look like this for the rest of the thing, which essentially means that your pressure and since elevation is changing, your pressure is going to change as well, and its change is going to be proportional to your elevation, right? So these are just 2 concepts that were introduced in your book, and I guess we just had to introduce them as well. But what are the conditions at which we cannot use the Bernoulli's equation? So we made some assumptions in the beginning of this chapter about the flow, right? What are those assumptions? The first one was the flow is incompressible, right? Another one was that the flow is inviscid, which essentially means that we are removing the effects of friction. Okay, and we also said it has to be along a streamline, and it has to be steady. Right? So essentially, when your flow is not compressible, is not incompressible, meaning that when it's compressible, you won't be able to use the Bernoulli's equation. So what is the criteria? Where can we set the limit? That after this point, the flow is compressible. We cannot apply the Bernoulli's equation. To find that criteria, we need to go back to the definition of compressibility. From chapter 1, if you recall, we defined this module as the bulk modulus that represented the compressibility of the fluid. It was dP, negative dP divided by dV by V. We can actually use the densities as well. So dP, you actually had a homework problem in which you had to use this, right? And this represented the compressibility of a fluid. Okay. The idea was the idea of an incompressible fluid was that this dP divided by d rho, dP divided d rho. I'm sorry, this is rho. This d rho divided by rho has to be 0, right? There shouldn't be any changes in density with pressure, with changes in pressure, which is not going to happen, right? In the real world, everything is compressible. So we have to set a limit. We usually use the limit of 3%. This is an arbitrary limit. So as long as your changes in density with any change in pressure is smaller than 3%, we should be able to apply the Bernoulli's equation. We can assume that the flow is incompressible, and we would be able to apply the Bernoulli's equation. Okay. So let's plug that value in the equation, the bulk modulus equation. We are saying the changes in density has to be smaller than 0.03, right? Smaller than 3%. And changes in density divided by rho is equals to your bulk modulus divided by changes in pressure, right? I'm sorry, changes in pressure divided. Okay. So changes in pressure divided by bulk modulus has to be smaller than 0.00, smaller than or equal to 0.03. And if you want to ask where did we get 0.03, in aerodynamics, we use actually 5% for this. So it means that this is an arbitrary number. It can be 5%, can be 3%, whatever, right? But we usually use 3% or 5%, okay? If you recall, for an isentropic flow, what we had was the bulk modulus was equals to kappa P. I don't know if you remember this or not, but this was the case. So we're gonna replace that here. Delta P divided by P is divided by capital P has to be smaller than 0.03. Where do you want to get from here? Okay, we essentially want to find a cutoff number, a limit that relates the velocity and pressure to this number. So we want to find a formulation that tells us that density multiplied by velocity divided by pressure, whatever, has to be smaller than this value for the incompressible assumption to be correct, right? So you don't need to go back. So you won't go back to do all of this analysis by yourself. Just plug in that number, plug in all of the values you have, and then you would be able to get a number. You would be able to determine whether the flow is incompressible or not. Who remembers what the value of K or kappa was for air? Or who remembers what this was in general? Is there anyone who remembers? Your chapter 1 or thermodynamics. In thermodynamics, for isentropic flow, we use gamma for it. I think so. 1.4, exactly, for air, right? And this is the ratio of the specific heats. Okay? So your delta P is going to be equal to 1.4 multiplied by P. It's going to be smaller than 0.03. Okay? We can move the 1.4 to the other side and get delta P divided by P smaller than 0.42, right? 0.042. Okay. How can we relate delta P to velocity? How can we relate pressure differential to velocity? Let's say we are talking about this pressure differential is a pressure differential between the stagnation pressure and the static pressure. All right? A stagnation and a static. How was this related to velocity? Does anybody remember? If you applied, what was the main characteristics of the stagnation pressure? Is the point at which the velocity is 0, right? In general, stagnation points are points at which velocity is 0, right? So if you apply the Bernoullis between this point and the static pressure at the same point, velocity is 0. So Ps minus P is going to be 1/2 rho v squared. Right? So your delta P, 1/2 rho v squared. And then you can move the 1/2 to the other side as well. And eventually you're going to get rho v squared divided by P has to be smaller than or equal to 0.084. What does this mean? It means that let's say you have one point and I tell you, can we apply the Bernoulli's equation to this point, right? What you need to do is that you need to have the velocity, you need to have the density, and you need to have the pressure for that point. Plug all of those into this equation, and this should hold true. That has to be, this value has to be smaller than the value on the right-hand side. And then you tell me that the Bernoulli's equation is applicable here. Do we have any questions? No. Okay. Good. And the last thing we want to discuss is what happens if your flow is not steady. A steady, we need the flow to be steady for the Bernoulli's equation to be correct. But what happens when the flow is not steady? What does it mean? It means that your properties are changing with time. essentially, I don't want to go back to all of the analysis. I'm just going to give you an equation. So if you recall, we derived the Bernoulli's equation using sigma f equals to ma. The idea was the dv dt part of a acceleration is going to be 0 because the flow is steady, right? But here we cannot make that assumption. So we have to include dv dt as your acceleration multiplied by ds plus dp 1/2 rho dv squared plus gamma z is going to be 0, right? So the only thing that is being added to your general Bernoulli's equation is going to be this part for an unsteady case. So if you were in an unsteady type of flow in which the properties or the velocity was changing with respect to time, then you have to make sure that you add this term to your Bernoulli's analysis. And then you have to integrate to be able to get all of the properties between the 2 points. Okay, so that's it for chapter 3. What we are going to do next is to solve the example problems. I try to include one problem from every part of this chapter. But in general, if you don't remember the equations we derived for a specific conditions, the point is you don't really need to remember any of the equations as long as you know the Bernoulli's and the continuity equation. As long as you know that between 2 points in an incompressible flow, this is true. Right? P2. All of the other things that we saw was variations of this equation, and also A1 V1 has to be equal to A2 V2. As long as you know these two, you should be able to solve any problem in this chapter. Okay, so let's start by the first problem 3.2. Again, these are already posted. The text of these problems are already posted on Blackboard. So I think everyone in class has a copy of the text of the problem. But if you're watching online, you can, if you're watching online, you can find this on Blackboard. The first problem that we want to solve is problem 3.2. And I want you to work on it for a couple of minutes, for like 2 minutes. It shouldn't take that long. And then we'll get to the solution. So the problem is telling us air flows steadily, which means that it is a steady state, right? Along a streamline. The second assumption was that flow has to be along a streamline. So 2 assumptions are already met. From point 1 to point 2 with negligible viscous effects. That's the third assumption, right? The flow is inviscid. We are neglecting the viscosity. And the following conditions are measured. At point 1, we have Z is 2 meters, P is 0 kilopascals. At point 2, we have Z is 10 meters, P2 is 20 newtons per meter squared, and V2 is 0. We want to determine the velocity at point 1. Okay. This is a very easy problem. It's a very standard type of problem you're going to get in this. From this chapter. Okay. Let's solve the problem. Do you have any volunteers to come to the board? Okay. No one? That's all right. So the idea is P1 and V2 are 0. We can rewrite this main equation as 1/2 rho V1 squared equals to P2 plus 1/2 rho V, this part is 0, right? GZ2. And we are given the Z here, 2. And we are also given, what else? So 2 multiplied by G, your gravitational acceleration. And we also have 1/2. Density is also given to us. I forgot to give it to you. That's 1.23 kilograms per meters cubed. And velocity at point 1 is also, is it? No. We want to determine the velocity at point 1. Pressure at point 2 is 20 newtons per meter squared plus G multiplied by Z2, which is going to be 10 meters. Okay. We can rearrange this, and your G is 9.81. So hopefully we all remember this. You can rearrange this and get your velocity V1 to be 13.7 meters per square. Okay. Let's solve the next problem. This is problem 3.3. This is a little harder. You have to be a little creative to be able to solve this problem. So we are told the water flows steadily. That's your first assumption that you need to make. The steady state conditions, the steady conditions, through the variable area horizontal pipe shown in the figure below. You have the center line velocity as V equals to 10 multiplied 1 plus X R feet per second. Okay, where X is in feet, and it is the distance from the pipe's entrance. Okay, point 1. And your length is going to be 3 feet. Okay, we are told to neglect the viscous effects. So which means that we are the implicit flow. We want to determine the pressure gradient as a function of X needed to produce this flow. So pressure gradient as a function of X. That's part A. Part B is telling us if the pressure at point 1 is 50 psi, we want to determine the pressure at point 2 here by 2 methods. 1, by integration from this pressure gradient, right? This is a function of X. And 2, by Bernoulli's equation, right? Yep, by applying the Bernoulli's equation. So the first thing you want to find here is to find the pressure gradient as a function of X. We already have the velocity as a function of X, which is that we can have the velocity, we can find the velocity at each location, right? But now we want to find the pressure gradient as a function of x. And I will give you a couple of minutes to think about this, but just as a hint, essentially, is that we are dealing with pressure gradient here, right? Bernoulli's equation did not deal with the gradients, but we had one equation before Bernoulli's equation that gave us all the gradients, right? And we integrated that equation to get to Bernoulli's, right? I don't know if you remember that, but it should be in your notes. And what was that equation? That equation was negative gamma sine of theta, and theta was the, I'm going to tell you what theta was in a minute. Partial P partial S equals to rho V partial S, right? This was the equation that we integrated to get to the Bernoulli's equation. What was this theta? If you recall, we started from a streamline, and this theta was essentially, let's say this is your horizon, right? Horizontal direction. This theta was essentially the angle your velocity vector made on a streamline with the vertical direction, right? This was the general equation that applied to a very small point in a flow. Then we integrated this to get to the Bernoulli's, right? Since we are looking for a pressure gradient, we have to use this equation. But how can we simplify this a little further? The first thing is that we are in a one-dimensional flow that is in the horizontal direction. So your ds, or partial s, is going to be only partial x, dx. Okay, that's one thing. And this also means that what does this mean for your theta? You have a one-dimensional thing, your velocity is always horizontal. Your theta is going to be 0, right? And there is no changes in elevation. So this part in general goes away. So you will end up with partial P partial X equals to rho V dV dx. See? Right? Is this clear? This is the same thing as the Bernoulli's equation. The only difference is that the Bernoulli is the integral form of this differential equation. Right? This is a differential form of Bernoulli's equations, and we integrated this to get to the integral form of Bernoulli's equation, or like the regular, normal Bernoulli's equation we have used. Okay. So we essentially have everything we need, right? We have the density, we have the velocity distribution as a function of x here, and then we can take the derivative with respect to x. I'm going to give you a couple of minutes to do this, and then we are going to do the solution together. Okay. So let's put all the values in. Your velocity is going to be 10 multiplied by 1 plus x. Your derivative of velocity with respect to x is going to be 10, right? And that's it. That's your gradient of pressure gradient. Of course, have to move the negative sign to the other side. Your dP dx is going to be equal to negative rho multiplied by 10. Okay, so let's get to part B. Part B is asking us to find the pressure at point 2 with a given pressure at point 1 using the integration of this gradient or Bernoulli's. And we want to see if those two methods are going to give us the same value. Okay, so let's do this. Let me rewrite this. Your dP dx is negative rho, or let's actually do this, negative 100 rho 1 plus x, right? And then let's move the x to the other side. You have negative 100 rho 1 plus x dx. Now we can take the integral from point 1 to point 2. Okay, the integral of the left-hand side is going to be P2 minus P1. And on the right-hand side, we are going to get negative 100 rho x plus x squared divided by 2 from x1 or point 1 to x2, right? So P2 minus P1 is equals to negative 100 rho. X1 is the starting point for your coordinate system. So this is 0, and x2 is 3 feet. So we are essentially going to get 3 plus 9 over 2, which is, this part is 4.5. So I'm just going to add this here, multiplied by 4.5. Okay. This is through integration. I don't want to give you the final value because that doesn't really prove anything to us, because we are not going to calculate it, right? As long as we get to the same expression, we are proving that the Bernoulli equation and this integration is going to give us the same value, right? So Bernoulli's P1 plus 1/2 rho V1 squared is equals to P2 plus 1/2 rho V2 squared. Okay. So P1 minus P2 is going to be equal to 1/2 rho V2 V1 squared minus V2 squared, right? There's also a rho here. So P2 minus P1 is going to be equal to rho, what is V1 squared here, is 100 1 plus x squared. And here x1 refers to this point 1, which means that x1 is 0. So V1 squared is 100 multiplied by 1, or 100. And then 100 multiplied by 1 plus x2 squared. x2 is 3, so 1 plus x2 is 4 squared is going to be multiplied, right? Multiplied by 1 plus x squared. X is 3, 1 plus 3, 4 squared. So we're going to get 16. Okay. Or here, 100 minus 1600 is going to give us 1500, right? Okay. What is 1/2 of the 1500? P2 minus P1 is going to be equal to 750 rho negative. Okay. Yeah, which is not the same result because I made a mistake here. We have this. Let's no, I didn't make any mistake here. Why aren't we getting the same results? 40 to the power 2 is going to be 1600, 100, 1500, and divided. Where did I make a mistake?
On the 4.5 on the right, it's supposed to be 7.5.
Oh, 4.5 plus 3, right? I forgot that one. Thank you. Appreciate it. Thank you. So yeah, we get the same result, right? 750 rho, 750 rho, which essentially means that the integration and the Bernoulli's equation are going to give us the same result. Okay. So let's solve. Let me see. Let's solve. Let's solve problem 3.36. And let's treat this as your quiz, right? If you are watching this online, just make sure to send me the answers for this quiz using PDF just after the class. And if you are in class, just get a paper, please. And then let's solve 3.36. I'm going to give you a couple of minutes. Problem 3.36 is the one that says streams of water from the two tanks impinge upon each other, as shown in the figure. Okay. But I don't think we're going to have enough time to cover all of this. So problem 336 of your book is telling us streams of water from two tanks impinge upon each other, as shown in figure below. Or the other figure as well. If viscous effects are negligible and point A is a stagnation point. So point A, velocity at point A is 0. Again, I think I have to stress this a little more. A stagnation point is a point where velocity is 0. So at point A, we are told that we have a stagnation point, your velocity is 0. And we want to determine the height h. And this is the figure. We have an open surface. This is point A. We have air here, and this pressure gauge reads 25 psi. This height here is 8 feet. 8 feet. We want to determine this height h. And this is also 20 feet here. Again, we want to determine the height h. Okay. Yeah, I'm going to give you like 5 minutes, 5-10 minutes to solve this. Then I'm going to get the papers, right? I will go through your solutions after the class, and whoever got it right will get a bonus, right? Since you guys don't volunteer to come to the board, I think that this is going to be my way of giving you the option to get the bonus points. If you got it wrong, you won't lose anything. Don't worry about it. But if you got it right, you will get a bonus point. As long as you have the procedure correct, you should be fine, okay? Not necessarily a correct final value. This also applies to people who are watching this online. I guess there are 7 students here. So the only condition is that I'm gonna like get the papers from you in, let's do 7 minutes, 5 to 4. 5 minutes to 4 p.m. or 3:55. And if you're online, make sure to send it to me by then. Okay, let's get the papers, and then we'll solve this together. Just pass your papers along, and then we can get all of them right here. Pass it along. Just get it to me in front. Okay. Thank you. Is there anyone who thinks they got it? No one? You don't have to come to the board or answer anything. I just want to know if there's anyone who thinks they got it. So, one person, two people. Okay. That's good. That's good. So let's name these points first, point 1 and point 2. What we're going to do here is write the Bernoulli's equation between point 1 and point A, which is this point here, right? And then we will write the Bernoulli's between point A and point 2 one more time. So let's do the first one. Bernoulli's equation, P plus 1/2 rho V1 squared plus GZ1 is going to be P2 plus 1/2 rho V2 squared plus GZ2. Okay. What are the informations we have here? The first thing we do, this is at PA, sorry. PA, VA, and ZA. Okay. We already know that point A is a stagnation point, so the velocity is 0. Okay. What can we say about the velocity at point 1? This is a free surface, and velocity at point 1. We can write this equation between point 1. Let's call this point 3 here, and point 3. Area at point 1 is much larger than area at point 3, which means that the velocity at point 1 is much smaller than the velocity at point 3. And this is a free surface. We usually assume the velocity of the free surface is 0, which is a very reasonable assumption. So velocity here is also 0. What about P1? This is a free surface exposed to the atmosphere. So the gauge pressure is the atmospheric gauge pressure, or 0. Okay. So your pressure at point A is going to be equal to G multiplied by Z1 minus ZA, right? Which is the H we are looking for, right? So PA is going to be equal to GH, or H is going to be equal to P divided by G. I'm sorry. PA divided by G. Okay. Is this clear? Yes. And let's apply the Bernoulli's equation between point 2 and point A again. Second time. Let's write it. P2 plus 1/2 rho V2 squared plus GZ2 is equals to PA plus 1/2 rho VA squared plus GZA. Here we have the Z2, 8 feet. 8. We have the ZA, 20 feet, right? We have the velocity at point A, 0. What about the velocity at point O, point 2? What can we say about the velocity at point 2? Here, on this air surface. We can apply the same analysis we did here. So we can safely assume the velocity at point 2 is also 0. So this will cancel out. And P2 is going to be the pressure you're reading at this gauge, 25 psi. Okay? And we actually have the value of PA, right? So GH. Let's plug those in. I'm going to write it up here. So 25 plus G multiplied by 20, by 8, sorry. Multiplied by 8 is equals to G multiplied by 8 plus G multiplied by 20. Okay? We could have actually used the heads, P divided by gamma, V squared divided by 2G, all of those things, and get to the same conclusion. It should give you the same value. You plug in the values you have for G, and then you are going to calculate your H, which is equals to 45.7 feet. What does this mean? This essentially means that if you want to get on a stagnation point at point A, this surface has to be 45 feet above point A for this specific condition. Okay? So do we have anyone who was going towards the correct solution, was moving towards the correct solution? Okay, so one person. Then you get your name to me after the class. I will give you the bonus point. And I don't need to go over all of your solutions, okay? So, what time is it? Oh, it's already 10 minutes. Do we have any questions? No. So, this will be it for chapter 3. What I'm going to do for Thursday, because Thursday is a wellness holiday, and you don't need to come to the class. It's a holiday, so there is no class. But what I'm planning to do, I can't promise anything, is to solve your homework, to like record a session essentially with the solutions to your homework 2 problems and the solution to the rest of these problems, and post it on Blackboard, post it on YouTube, and post a link on Blackboard. So you can go back and watch it if you want to. If you don't want to, you don't need to watch it. And yeah, I will post it on Thursday, but you will have access to it throughout the semester. So whenever you need to go back and watch it, that's the plan, if I have enough time to do this. But yeah, and we are going to start chapter 5 on Tuesday in a week, and you will have your first exam in essentially 16 days. And your next exam is going to be March 11th, right? It will be Thursday, 2 weeks after, like this Thursday. So in 2 weeks, essentially. So I guess that's it, right? Yeah. Have a good day.